Section 4.7, row space, column space, and null space. It is possible to take a system, an m by n system, convert that into a matrix, look at the coefficient set of the matrix, look at the individual rows, and look at the individual columns. The rows are said to form the row space, and the columns are said to form the column space. And so, by definition, let some matrix A be an m by n matrix. Then the subspace of Rn spanned by the row vectors of A is called the row space of A. And then the subspace of Rm spanned by the column vectors of A is called the column space. If you look at Ax equal to 0 at the homogeneous linear system, and to solve that, we say that its space is called the solution space. And there, the subspace of this particular space of Rn is called the null space. So the null space of A is tantamount to saying the solution space of the homogeneous system, Ax equal to 0. The superposition principle for vectors is important. It is said to hang the framework for this course and differential equations. In terms of solving a differential equation, the solution is said to be based on the superposition principle. So that concept comes from linear algebra. Differential equations is actually a subset of linear algebra. So every solution, the general solution, is said to consist of a particular solution and also the complementary solution. The complementary solution is found by letting Ax equal to 0 or solving for the homogeneous system. The particular solution is said to be from solving Ax equal to b. It's very tantamount to differential equations for a homogeneous differential equation and a non-homogeneous differential equation. For the homogeneous differential equation, you have a complementary solution that we'll call x sub c. And then for the differential equation that's non-homogeneous, there to solve it, we call its solution a particular solution. Because when you have a non-homogeneous differential equation, you have the terms equal to some function. That function can change. So for each time the function changes, you get a different particular solution. So we call its solution x sub p. But the general solution of Ax equal to b, in general, for all particular solutions, is said to be x equal to the particular solution, and actually is really the summation of the particular solution plus its complementary solution. Here, the framework for linear algebra is that the complementary solution consists of the basis for the solution space, which is no more than this linear combination of the basis here from capital S. And then plus x sub naught. X sub naught is said to be a particular solution to x sub p. That is, x sub naught solves Ax equal to b. There's an example here that's given, and I want to work that for you. Let me state these theorems, and we'll go through the theorems based on problems so you can definitely understand what's going on. Theorem number 1, elementary row operations do not change the null space. The elementary row operations do not change the row or column space as well. That's why you can use your graphing calculator to take the matrix, reduce it using row echelon reduction, and then from there be able to get the solution for the basis for the row space or the basis for the column space. When the matrix is reduced to row echelon form or row reduced echelon form, you look for on the main diagonal where the leading 1 would be. The leading ones tell us that that particular row or column is in the so-called row space or column space. Matter of fact, let me state it again and emphasize. when you reduce the matrix and you have the leading ones along the main diagonal, that tells you that that row is a basis for the row space. It also tells you that that column is a basis for the column space. If you look on that same matrix in its reduced form and you don't have a you don't have a 1 on the main diagonal, where you get a 0 on the main diagonal, then that particular row is said to be in the null space. Okay, does that make sense? So the key is take the matrix, reduce, look for the leading ones. The leading ones, its row, its column gives you a basis, respectfully, for the row space and the column space. The corollary is pretty interesting. The corollary is said to be a consequence that correlates to a main idea, something that corresponds to a main theorem. So we have the theorem above, the corollary that comes from that is that let A be a matrix reducible to row echelon form. The original corresponding rows or columns of A that corresponds to the rows with leading ones also forms the basis for the row column space. Here's what we're saying. If you take the original matrix and you reduce it to row echelon form, and in that reduced form you can see the leading ones along the main diagonal. Well, if I get a leading 1 in the first row, I have a leading 1 in the second row, that means that the original matrix, row 1, the original matrix, row 2, also forms a basis for the row space. So either you can take the original matrix rows for the basis, or you can take the reduced echelon form for those rows. Doesn't matter. Still a basis. Okay. So now let's look at some problems here. A vector B is said to be in the column space of AX equal to B if AX equal to B has the unique solution. Determine whether B is in the column space of A, and if so, express B as a linear combination of the column vectors of A. Now here's the first thing you want to do. Take the matrix A, reduce row echelon form on your graphing calculator. So on our graphing calculator, A is reduced to this. Here's what I did. I took AX equal to B and I reduced that this is AX equal to B reduced. Now I reduce that on my graphing calculator. This gives me, you recall from chapter 1, no solution. Because that last row gives me 0 equal to 1. Right? That is tantamount. Yes, sir. With AX equal to B. I get this. Yes, sir. Well, there's no solution, right? right? So there's no solution, then obviously B cannot be expressed as a linear combination of the vectors of A. All right. So for the next problem, I'm going to reduce it down. So and here so now what this means is that I can write B as a linear combination of the rows of A by this way. In other words, this implies that C sub 1 is equal to 1, C sub 2 is equal to -3, C sub 3 is equal to 1. These are the values that I get here. And so I have C sub 1 times row 1 plus C sub 2 times row 2 plus C sub 3 times row 3 is equal to B. B here is 5, 1, -1. That is, C sub 1 is 1 times row 1 plus C sub 2 is -3 times row 2 plus C sub 3 times row 3. That's equal to this B vector, 5, 1, -1. Now, number 3 makes use of the superposition principle. So here, that any solution the general solution of any system can be written as a linear combination of every particular solution and its associated complementary solution. So here, that means that X, this general solution, is equal to XC plus X sub P. The particular solution plus its complementary solution. When you solve for AX equal to 0, and that solution space here gives you X sub C. When you solve for a particular solution of AX equal to B, you get X sub P, But then the general solution of Ax equal to b for all those guys would be x sub c plus x sub p. So here, a particular solution says that let b equal to this vector. Here's an example. I don't know what all that was. You see this matrix A is a system. Here B is 5, 1, negative 1. For each B we get a different solution. We get different values here for C1, C2, and C3. Right? So here C1, C2, and C3 is said to be a particular solution that corresponds to 5, 1, negative 1. But let B be another vector, 8, 6, 12. Then I get different values for C1, C2, C3. How many B values that I can have? Infinitely many, right? So the particular solutions can be many. So the actual write-up for it is that the general solution is the summation as I goes from 1 to n of x sub pi, and then plus x sub c. So because there are many of these particular solutions, and to make sure that you don't see that x sub c is in the confines of the summation, x sub c has its own summation because it consists of a basis. So this is x sub c plus the summation as I goes from 1 to n of x sub pi. So that's to really say it in detail. And I should have put it down here for the general solution. Here, this x is equal to x sub c plus this summation. Well, so here it says find the vector form for the general solution of ax equal to 0. But that's where when you take the matrix and you reduce it down, this is where they got x sub 1 equal to this negative 3r plus 4s, x sub 2 is equal to r minus s, x sub 3 is equal to r, x sub 4 is equal to s. That gives us here this x sub c. So x sub 1 is negative 3r plus 4s, x sub 2 is r minus s, x sub 3 is r, x sub 4 is s. So we get negative 3, 1, 1, 0 times r plus 4, negative 1, 0, and 1 times the s. So x sub c is equal to here, this basically, if you think about it, this is some c sub 1 times v sub 1 plus c sub 2 times v sub 2, where v sub 1 is this vector here and v sub 2 is this vector there. So again, you understand this itself as a summation of terms. You can write it as such if you wanted to. This is some fixed number. Here this would just be 2 of c sub I times v sub I. Now then it says find a vector form for the general solution of ax equal to b. Well, first we find the solution form for x sub p. Find its solution form, where x sub p, the particular solution for this problem, is given here. Suppose that x sub 1 is equal to negative 1, x sub 2 is equal to 2, x sub 3 equal to 4, x sub 4 is equal to negative 3, is a solution of a non-homogeneous linear system, AX equal to B. So that's just one particular solution. So we write that negative 1, 2, 4, and negative 3. I think I got those right. Yes. So therefore, the general solution for AX equal to B is X is equal to, we say its particular solution plus its complementary solution. The particular solution is negative 1, 2, 4, and negative 3, plus now its complementary solution, negative 3, 1, 1, 0, times R plus 4, negative 1, 0, 1 times S. So this is for part B, and then for part A, that's what we want. Okay? So the general solution is its particular solution plus its complementary solution. The complementary solution never changes. The particular solution will change for each different value of B. Now find a basis for the null space and row space of A. And you take this matrix, reduce it down, and it's okay if I did it before, we'll do it again. One, 0, 0, 0, 1, 0, negative 16, negative 19, and 0. Now it's easy to get the row space first. The theorem above said that when you reduce the matrix, you see the leading ones, those particular rows become a basis for the row space. So R1 and R2. Now the basis for the null space has to be solved the basis for the null space is the same as the infinitely many solution set. Same thing. So here we take this matrix. Notice that along the main diagonal, here I have a 0 at that A33. So that tells me that that variable x sub 3 is a floating parameter. So we let x sub 3 equal to t. And look at the first row. This is x sub 1. If I can go ahead and write it, it's equal to 16t. Do you see that? Does everybody see that? I mean, tell the truth if you don't see it. X sub 2 is 19t. Now, how come x sub 1 is 16t and not negative 16t? Yes, sir, that's what I'm talking about. Matthew, he comes in a couple minutes past the time, but he comes in answering the problem. Man, I love that right there. Yes, sir. Beautiful. Did y'all hear what Matt just said? Thank you, Matt. Can you catch that, Matt? And the question is, can I throw? And thank you. I almost didn't make it, but yes, sir. Okay, very good. So if that be the case, then we say that here, that x for the basis for the null space is equal to the x sub 1, x sub 2, and x sub 3. Here, x sub 1 is 16, x sub 2 is 19, x sub 3 is 1, that's all times t. So here, the basis for the null space, why is it called null space? Because you're trying to solve ax equal to 0, with 0 set to be the null. Right? So the basis for the null space is this vector 16, 19, and 1. You can write it like that. Several ways you can write it. You can say here or 16 comma 19 comma 1, right? Or you can write it as a matrix 16, 19, and 1. Okay. It's the same argument for part B. We reduce the matrix. Reducing this gives us 1, 0, 0, 0, 0, 0, negative 1/2, 0, 0. So the basis for the row space is just only the first row. Because that's the only row with a leading 1. The basis for the row space. Now we find the basis for the null space. So here, what is wrong with this computer? So we have x sub 1 minus 1/2 x sub 3 equal to 0. X sub 2 and x sub 3, there's a 0 on the main diagonal. Doesn't mean they go out. It just means that their values are arbitrary. So we let x sub 2 equal to s, x sub 3 equal to t. If that be the case, x sub 1 is equal to the 1/2 t. So x is equal to x sub 1, x sub 2, x sub 3. X sub 1 is 1/2 t. X sub 2 is s. X sub 3 is t. It's going to use the associative property. So here I have 0, 1, 0, s. Associate the like terms, the s's together, the t's together. Here 1/2, 0, and 1 times t. So you see that the basis would be 0, 1, 0. This is the basis for the null space. And 1/2, 0, and 1. Now you remember a couple days ago we went to section 4.8, talked about the rank that is the number of vectors in the basis. So if we had the same question, which we will on these same problems, if we ask what's the rank for part A, the rank would be 1. I'm sorry, the rank would be 2 because I had 2 vectors for the row space. So the rank goes with the number of vectors for the row space. The nullity goes with the number of vectors in the null space. So the rank plus the nullity should give you n, what that space allows for Rn, right? If it's a 3 by 3, n is equal to 3. So notice here that the rank would be 2 and the nullity would be 1 because I only had one of those vectors, right, for the null space. So 2 plus 1 equals 3. For part B, we only had one vector that was a basis for the row space. So its rank would be 1, and then its nullity would be 2. We had 2 vectors for the basis for the null space. Okay. Number 5, the matrix is in row echelon. See, the matrix. I need to go back and correct my language. The matrix in row echelon form is given. Yeah, the matrix in. I don't know how that slipped me by. And why is it all caps? By inspection, find a basis for the row space and for the column space of the matrix. Well, that's good for us because the work has been done on the graphing calculator. I look for my leading ones, and those rows become a basis for the row space. So here, the row space basis would be R1, and R2. Column space basis would be C1, in column 2. Okay. Should have been another question here. I don't know what happened to it. The question is, find a basis for the row space that consists of rows from the original matrix. I don't know how come that question didn't get I have it on the sample exam, but I thought I had it here, but I don't. Find a basis for the subspace of R4 that is spanned, this is number 6, that is spanned by the given vectors here. Now, this question is misleading because these vectors do not span R4. Right? Because to span R4, you got to have 4 vectors. Right? I got 3 vectors, so they don't span R4. But you got to go back and read what it says. The language is very significant. Find a basis for the subspace of R4 that is spanned by the given vectors. So we're not trying to span R4. We're trying to span vectors that can be produced by writing these 3 vectors as a linear combination. You see that? A little bit different. Find a basis for the subspace of R4 that is spanned by these given vectors. In other words, what do these 3 vectors, what vectors can they produce? So now What they're saying is, can you find the skeleton framework for these three vectors to give you any vector of their form only? And because of that language and how it's written, the way that you will solve this is you will take these vectors just as they are, and watch this. Each vector itself becomes a row and not a column. They don't stand up. There's something queer about these vectors. I told you vectors are like men. They want to stand up. If a vector doesn't want to stand up, there's something wrong with it. And because of that, this problem is not on the test. But I want to go ahead and show you. So you take this guy and you're going to reduce row echelon form. You can reduce row echelon form, or you can reduce echelon, row echelon form on your graphing calculator. But we're going to keep the vectors as rows to reduce. Reduced down to 1, 0, 0, 0, 1, 0, 1, negative 5, 1, negative 1, negative 2, negative 1/2. So here, this basis for this subspace that's spanned by these three given vectors would be R1 equal to 1, 0, 1, negative 1, R2 equals to 0, 1, negative 5, negative 2, R3 equals to 0, 0, 1, negative 1/2. Okay. Again, I won't put that one on the test because it does not follow the typical pattern in terms of how we try to manipulate these vectors. We understand that the vectors that are written as a as a row in that sense is actually a column, and so the vector becomes the transpose when you actually write it out and when you also put it into your graphing calculator. These guys don't stand up. But that's the only way that you can produce some basis for R4 and not R3. If you stand these guys up, then you're producing something for R3 and not R4. So, any questions for this section? Well, let's look at 4.8 and then just for about 5 minutes, then spend the rest of the time for 5.1 on eigenvalues and eigenvectors.